In this lecture, we'll look at the exec family of system calls. These system calls are how a brand new program is started, generally by a forked copy of a parent process, as we'll see in our example. The system calls exec-L, exec-LP, exec-LE, exec-V, exec-VP, and exec-VPE, which we will collectively refer to as the exec calls, are perhaps the most interesting Unix process control calls, along with fork. These are the calls that start a new executable from scratch, each in slightly different ways. Our first example is the exec-L call on line 10 of the code. Now this line is done in a child process due to the fork on line 9. The child's call of exec-L takes as its first parameter the name of another executable, in this case the standard system command /bin/echo, which simply prints its command line arguments to the screen. If you run the command echo hello world, it prints to screen hello world. That makes an easy executable to play around with here. But to be clear, any executable could be provided for the first argument, whether a system command or a user program. Now, the rest of the exec-L parameters are command line arguments for the new executable. Exec-L is variadic, so you may pass as many string command line arguments as you like, terminating the list with a null. Exec-L then runs /bin/echo with the command line arguments given. But exec-L doesn't create a new process. Instead, the exec-L call causes the child process itself to load the new executable, wiping out the child's current code, data segment RTS, and indeed its entire process space, so that the child process is at the start of a new /bin echo executable with no memory of its prior code, data, etc. Another science fiction metaphor may be useful here. An exec call is a brain wipe, a complete replacement of personality and memories with an alternate personality and memories, and one starting at birth, so to speak. So, the complete science fiction metaphorical description of how a new program starts in Unix is: a parent process steps into the transporter, fork, and gets duplicated. The child initially has all memories, data, and personality or code of the parent. It knows it's the child only by the return value of fork. After possibly doing some preparatory setup, examples of which will appear in later lectures, the child then steps into a brain wipe machine, an exec call, and steps out as a brand new person, starting as a baby, a process starting at main. Here's question 1. Line 11 announces that the exec-L call failed. Exec calls can fail, for instance, as the result of a bad file name for the first parameter. They return -1 upon failure, and they set error no. But our code doesn't even check this return value. It simply announces an error. Why is this reasonable? Don't we need at least an if check to see if the exec-L succeeded here? Coming back from a pause there. This is sort of a reality check to see if you got the picture of what I was talking about with brain wipe. If the exec-L succeeds, there is no way line 11 will be executed. It can only happen if the exec-L failed. It replaces the entire child process space, current code and all. This includes the runtime stack and any memory that we just called exec-L. Recall that fork is odd in that one process makes the call and two processes return from it. By contrast, an exec call is odd in that one process makes the call, and if the call is successful, no process returns from it. If you return from it at all, that means you didn't get your process space wiped and replaced, which means the exec failed. If you step out of the brain wipe machine, and your first question is, was the brain wipe a success? The answer is no. For this reason, it's common practice to put error handling directly after an exec call with no check of the return value. Let's Question 2. Assume that you're running a program that was started via execl, per our example here. In the new program, a call of getPID returns your PID, which is, let's say, 1234. How would you get the PID of the process that provided your command line arguments? What PID number process provided your command line arguments? And coming back from a pause again, this is a bit of a trick question. Really, it's the same thing as before. The PID of the process that provided your command line arguments is 1234 because you arranged your command line arguments by passing them to execl just before you brainwiped yourself. You don't remember doing so, of course, but it wasn't your parent or some other process that did it. You did. Your command line arguments are like a note you wrote to yourself and pinned to your shirt before stepping into the brainwipe machine. It's like the protagonist in the movie Memento. You don't remember writing the note, but it came from you. Now, with that introduction then, let's walk through the entire exec.c example. Note that the particular output at the bottom here may differ from run to run and from machine to machine because the execution speed of the 3 child processes that we're going to create may vary. In our example, we first see the parent announcing itself on line 14 of the code, or line 32 of the output, after the first fork, printing the child process ID of 29170. Now that child does the execl call of echo, the output of which actually appears down here on line 33. And question 3, by the way, what happened to the echo command line argument from the execl call? Why wasn't that printed by echo? Going back from a pause, recall that the first command line argument is presumed to be the name of the program being run. Echo doesn't print its own name, only the second and later command line arguments. Interestingly, it is only by convention that the first command line argument is the program name. We could have replaced echo in that execl call by anything we liked. The OS does not enforce any rule regarding the first command line argument, and in particular it does not use the first parameter of the exec call as the first command line argument. That first execl parameter is just the file name containing the executable to be run. It's not a command line argument. Now, our next exec call is execlp on line 16, which, as you can see, is performed by a child process, a second one, created by this fork here on line 15. Now, this version of exec uses the path environment variable to interpret its first parameter. So we don't need to add /user/bin before printenv. execlp will automatically search the path variable for the parent directory that contains the printenv executable, which happens to be user bin in this case. Recall that printenv is the Unix command to print the current environment from an earlier in-lecture question. We'll be using it to illustrate exec calls that change the environment. Now, the line 18 printf from the parent shows on line 34 because the parent outraces the child process, which is PID 29171, that was created on line 15. The result of the execlp call by that child, the printenv output, appears on lines 36 through 45 down here. Now, a third execl call, or exec call, this time to execle, appears on line 20 after a third fork. The line 22 printf from the parent, whose output is on line 35, indicates that the third child has PID 29172. So we've now created 3 children with PIDs 29170, 171, and 29172. Now this third child also execs printenv, but this time it explicitly gives the full executable path name as its first parameter, because the exec LE system call doesn't consult the path. And exec LE adds a final parameter here pointing to a standard block of char pointers to environment strings complete with a final null pointer. We've set an example up in mock envp here on line 7. So look and be sure you understand what we're doing there. That's a mock environment variable structure, double character pointer and all. As you can see on lines 47 through 49, this second call of printEnv prints this supplied new environment. So you can see that the environment a new program gets is determined by the exec call that starts it, just like the command line arguments are. Now, we've illustrated 3 of the 6 exec calls, each with its own rules about path, passing the environment, etc. You're probably finding it a bit hard to remember them all, but there is actually some rhyme and reason to their names. They're all named exec, followed by some set of suffix letters, having the following meanings. P. Use the path environment variable when interpreting the first argument. L. Accept command line arguments as a list, a variadic list of string parameters after the first argument terminated with null. E. Accept a final double char pointer parameter giving a new environment. V, and this one we didn't use in the code, accept command line arguments as a double char pointer to a block of pointers, like argv, instead of as a variadic parameter list. This is useful when the number of command line arguments may change or must be dynamically computed. Not all possible combinations of these exist. All you have are the 6 exec calls given at the start of the lecture. Question 4, by the way, some combinations wouldn't even make sense. Why would you not expect an exec LVP, for instance? Coming back from a pause, because you can only pass command line arguments as a variadic list or as a double char pointer. It makes no sense to pass them both ways. Now, the final loop on lines 27 through 28 here waits for all 3 children, per our earlier discussion on parent processes waiting for child processes. And by the way, if you pass null for the status parameter, wait doesn't return any status information, just the PID of the finished child. Now, the results show on output lines 46 and 50 and 51. So here's question 5. Why don't all 3 of those lines show at the very end? Would it have been possible for all 3 instead to show just after line 46? So how come they're not grouped at the end? And alternatively, could they all have been right after line 46? Now, to answer this, coming back from a pause, you really got to think about the possible order in which things might run with the parent and the 3 children and their execs that we've done in the example. So consider that. Now, as mentioned earlier, we cannot ensure the relative speed at which different processes run. The first wait call shows output as early as line 20 or 46 here, because the parent process has already done all its forks and has reached the final loop before the 3rd child started performing printEnv. The 2nd child is done by then, and await returns its PID. You can see that is the PID of the 2nd child. It would have been possible also for the wait on PID 29170 to be printed on line 47, since the 1st child is also done. So this line 51 could have been up there. The 3rd wait, however, cannot return until the 3rd child is done, which would have to be after line 49. And note, the 2nd child's wait returned before the 1st child's. This is perfectly possible. Wait only promises to return the PID of some child that is done. If several are done, it picks one at random, not necessarily the first to have finished. Question 6. Might a wait output line have appeared just after line 38? Could we have had a child done message as soon as line 38? And which one, if so, or why not, if not? Coming back from a pause there. Sure, the wait for 29170, that first child, the echo process, which is all done by line 38 in the output, or actually, I'm sorry, 33 in the output, might appear right after line 38. Nothing prevents the parent's output line, by the way, from appearing in the middle of the output lines of the first printf. The parent and the second child that's doing that printf are separate processes, competing for the same screen. Now, this discussion is meant to show that the order of operations performed by simultaneously running processes really is unpredictable. Never count on processes to run in some order, unless the first is waited for before the second is forked. Assuming a particular execution order can cause very subtle bugs that occur only once in a blue moon when the order in which competing processes run is just right. Such bugs, where a race between one process and another, or one thread or another when we get to threads, where that race determines whether the bug happens or not, are called race conditions, and they're perhaps the worst sort of bug to trace and fix, because they are inconsistent, they are unrepeatable, and happen only sporadically.